So we're just using this thing here, k times, right? Because starting from 2k, we're going to step down k. We're going to step down k steps of 2, right, and go all the way down to a naught. Right? So at each time you multiply by -1, so at the end we get -1 over k. And each time you're stepping down from 2k minus 1 all the way down to 1. Right? And so you get this skipping factorial.
Is there a way to express that like with factorial notation wise?
So I sometimes see people use a double band, right, to say that this is skipping by 2s all the way down to the bottom. I don't mind if you use that, but I'm not sure if the grader will recognize it. So maybe explain it, or just make this what I mean by this.
I'm not sure that I'm following like the last step for the bottom part of the fraction.
Well, I think, right, at each step, we're multiplying by -1 to the 2k minus, right, a sub 2k is going to be -1 over this index minus 1, right? A sub 2k is going to be -1 over the index minus 1 times the guy 2 steps before.
Okay.
That guy, in turn, right, is -1 over its index minus 1 times the guy 2 steps before that guy, right? You keep on going, right? This guy is going to be, like this thing, is -1 over 2k minus 5 times a 2k minus 6, right? You go all the way down to, you go down k steps, and in the end you get down to a0, right? Right, and each time you multiply by something like this. So 2k minus 1, 2k minus 3, 2k minus 5. And that's these things here. 2k minus 1, 2k minus 3, 2k minus 5, blah, 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 all the way down to 5, 3, 1.
Oh.
I've written them in the opposite order, and that's what confused me.
Oh no, I thought it was like 1 times 3 times 5 times 7 times blah blah blah.
It is.
But then it gets to, but that's not multiplied by, I mean it is multiplied by 2k minus 1.
Yes.
But it's also multiplied by 2k minus 3 times.
Yes, yes.
I was somehow thinking that the first numbers were going to make like 2k minus 3.
No. Those are, so all these guys are still included. I just didn't write them. They're in the dots.
Yeah.
Okay. Okay, so what do we see about the even coefficients? That here they are, right? The even coefficients of a solution are like this, right? They're all multiples of a naught. In fact, we know exactly the multiples. Okay. And then for the odd coefficients, same sort of thing. A sub 2k plus 1, say. Well, that's going to be -1 over the coefficient minus 1 times the guy who's 2 steps before. Right? So we get 2k minus 1. Right? We get, again, -1 over 2k. We get -1 over the coefficient of the index minus 1 times the guy that's 2 steps before that. Right? All the way down to the bottom. Right? You get -1 again to the k over, well, you see what's going to be. It's going to be 2k times 2k minus 2, 2k minus 4, blah, 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 all the way down to 2. So 2k minus 2, all the way down to 4, 2, and then you stop at 2, and a1 at the end. So this says that we know what the even coefficients are, right? And we know what the odd coefficients are, so we read it all up, right? So the recurrence relation, this thing they call it the recurrence relation. And yeah, and then this is also sort of like an initial, a first recurrence relation. Okay, so, and those things together, basically tell you how the coefficients grow, right? Once you have a naught, then a2 grows off of it, a4 grows off of that. That's how these things grow off of it. You start with a1 also, and everything else is determined by that value. Okay. And so, what does that tell you? That says that that the solution, right, y sum k, is going to be summation let's say the even terms. So a sub 2k is going to be -1 to the k 2k minus 1 double rank a1 times x to the 2k. Right? That's the coefficient. Right? A sub 2k is the coefficient of x to the 2k. Right? Plus summation -1 to the k over 2k double bang a1 x to the 2k minus 1, 2k plus 1, because that was the coefficients for 2k plus 1. Here k is ranging from 0 to infinity, and here k is ranging from, again, 0 to infinity. Okay. Everyone right? I'm just going to do one small thing. I'm going to move the a constant down because it doesn't depend. Okay. And this is it. These. What you see is that any analytic solution, we know that the solutions are analytic from the theorem. We see that any analytic solution is expressible as a linear combination of these two functions. Right? This is the general solution. Right? We've got two functions here, and linear combinations. A0 and A1 are whatever we choose them to be. Right? We could choose them to be whatever, and then everything else depends on that. Right? So we see that these guys are the fundamental set of solutions for the homogeneous equation. So it's pretty cool right now. It's cool. Yeah, awesome.
So in some ways, like the hard part is identifying, like once you get to the power series part, like doing the odd even function part of it.
What's the hard part?
Well,
I'm not sure what the hard part
I can't easily look at that and do what you did. I think I just don't have.
But it's not deep.
Right.
You see, what skill was involved? Taking the derivatives, that's easy. Plugging them in, that's easy. Combining them together, that takes a little bit of doing. But once you do it like 2 or 3 times, then that's about it. There's not much depth to that ability. It's all it is what index do we want to start from? What's the common index that they all start from? Take out the other terms. So you remove the constant term. So maybe you need to remove the first couple powers to have them all start at the same power. You reindex them to make it all one common power series. Then you have the power series equal to 0, so you know that the coefficients equal to 0. That gives you the sort of initial recurrence relation and later recurrence relations, right? Those recurrence relations, then you use them to figure out the coefficients. I guess that's maybe the hardest part,
Yeah, that's what
right?
I'm saying.
But again, it's not deep, right? You just say, well, look, these guys fall into the evens and the odds. There are some examples. I think there's one example in the book where they fall into three streams, right? There'll be the guys who are who depend on A naught, the guys who depend on A1, and guys who depend on A3. A2, excuse me. Right, so, and then you just figure out what they are, just by doing this sort of, just by doing what we did, just multiply, oh, this is what it is. And then you put it back together. So it's not, none of this, it's simply a sort of a skill of manipulating power series. Which is okay, is an okay skill to have, but not particularly, not one that will get you far. You can't make it really well.
So we're going to go through all the steps we did for every problem like this?
I'm afraid so. So again, solving this sort of problem is exactly this. You create it, plug it in, figure out the recurrence relations, figure out the coefficients, and then put it back together. Right, so these guys are these guys F and G, right, are the fundamental set of solutions. And like we said, this works as long as we are in the common interval of convergence of those two analytic functions around an ordinary form. Okay.
So the recurrence relation is the fundamental set. So each recurrence relation is like one of the, is that what you're saying? Or not? Because like, you said the recurrence relation was like a sub n plus 2 equals negative 1 over n plus 2. So is each one of those, like, so can we apply the Wronskian to this or not?
Yes, we could. Right? These guys are going to be linearly independent. These are going to be linearly independent functions. You could apply any sort of linear.
Would we have to?
Would you have to? No. So you're wondering how do you know?
Yeah. Because the recurrence relations are just like mod, like one's even, one's odd.
I think that will give it to you. Yeah, that's enough. Right? That one is even, one is odd. But sort of. You sort of know it like this, and this is sort of the linear algebra way out of it, so the general abstract way out of it. You know that the solution space is two-dimensional, and you have two guys who span the solution space. They have to be linearly independent, right? Because if they were dependent, they would be one-dimensional. Their span would be one-dimensional, right? So from a linear algebra perspective, it's obvious that these guys, because their span is the solution space, you know that you know that every solution to it must be a linear combination of these things, right? So you know that their span is the two-dimensional solution space. Well, there are only two of them, so they can't be linearly dependent. If they were, their span would be only one dimension. So you don't have to